Yesterday it was 2. You told us after getting
I think you didn't mention shallow topological minors, no? I think yesterday. And it exists. We will not cover it, but it's very useful in theory as a tool. Still mention it. Start. Anyway, I'll start slowly so people will come late. Catch up with new definitions. Good morning, everybody. So, okay, the focus, I will start with a little bit of complement or going back to yesterday's lecture. And then the main topic of today will follow. It will be generalized coloring numbers. So these are more, not really generalization of coloring, but more generalization of the actual coloring number, so Shagnik mentioned yesterday, which is roughly the degeneracy plus 1 of the graph. So this will be based on ordering of the vertices. And this is super nice because you can use this notion to characterize graph classes of boundary expansion. And the proof techniques are really nice using this. And actually, most of the things we are going to cover in the lecture will follow from this tool afterwards. They will introduce it, and in the next, I think, 1 or 2 lectures, probably 2, we'll give essentially applications of these techniques. But let's recap. The three, I think 3 important definitions of yesterday are, well, the shallow minors or bounded depth minors. Right. So you just take a normal minor, but you restrict when you take a minor model, whatever you construct. You restrict to bounded radius. If the radius is d, this is a d depth minor or a d shallow minor. Okay, so this is important to get. Of course, you can still delete vertices and edges. And this is also important. And using this notion, we defined the greatest reduced average degree, denoted lambda d, of a graph, which is the max of the edge density, meaning number of edges by number of vertices, of d shallow minor. This definition.
So the minimum d doesn't have any special name.
Sorry?
The minimum d such that it's a d shallow minor. That doesn't get any special name. Just one more.
question, I don't know. No, I don't understand. The minimum t, I mean, for every d, you fix d.
No, for a given h, let's say.
For given h.
Yeah. I mean,
for given h, right? I mean, you fix the h and you see how you can obtain it,
right.
and you vary d.
Yeah.
I don't know. So usually we put the outside the other view point where we fix d, and we look at what can we get.
Okay.
Right. And so this definition is the basis of the definition of a graph class of bounded expansion. So bounded expansion essentially means that for every fixed d, your d shallow minors have bounded greatest reducer. So in other words, there exists a function which depends only on that graph class, which takes a d, and will give you an upper bound f of d on the density, edge density of your shallow minor. Whenever you contract with balls of small radius, that should not be very big. And we saw that you can relax this definition by instead of the average BE, you take the clique number and then you get Nova dense graphs. We'll not cover them, but it's nice to keep in mind that essentially most of the definitions and things we are doing here can be extended to Nova dense. It's just that well, the definition is very similar, but the techniques are more involved. But essentially it's the same flavor. If you're interested, you can look it up and see. The theory there is also very nice, but more complicated. Okay, so bounded average degree, as we saw yesterday, is since you're taking minors, you can also think of it as bounded degeneracy, or maximum average degree. This is basically maximum average degree with a factor of 2, which is the difference. Okay, so what Shakin said yesterday.
I'm sorry, I have one question. You said coloring number is degeneracy plus 1.
Yes.
I think yesterday we defined it as degeneracy itself.
Yeah, so but I think the standard definition is degeneracy plus 1 because this is essentially the bound you get on the chromatic number.
Okay.
So the chromatic number is at most degeneracy plus 1, right? Because you just greedily color from left to right. So if you had, you have this ordering, right? So the definition of, let's recall it actually. So if you have an ordering sigma of your vertices, what will be degeneracy of the degeneracy of G is basically the minimum over all sigma of the maximum number of backwards neighbors. Of a vertex. Okay, that means you want, let's say, most k neighbors that you're seeing, so that you're already seen in the ordering. I mean, you might have many more, but they have not been seen yet. So it means if you start greedily coloring from left to right, first vertex gets color 1, obviously. You take always the minimum. Then the second vertex gets the smallest color which is available in the neighborhood, and so on. And since everybody has a backwards degree at most k, that means for every vertex at most k colors are unavailable. So you can color with k plus 1 vertex. So this k plus 1 is called your coloring.
So yesterday when you proved the max average degree is between coloring number and twice coloring, it's actually between degeneracy and twice degeneracy.
Maybe.
Is that right?
Yes, I mean, because, Shankit used he said that coloring number is degeneracy, which is fine, you can define it like that. But I prefer to define like this because it will fit with my theory of today. And I think traditionally it was designed like that. So coloring number will be degeneracy of G plus 1, right? And this is, so we know that the chromatic number is at most this. Okay, so don't confuse chromatic and coloring number, even though it's almost the same, but this coloring but I will come to that a little bit later. Let me still give some remarks about yesterday. So shall we give a nice example of that the h minor of a graph, if you exclude a minor h, a fixed minor h, these will satisfy this definition. And in fact, even stronger in the sense that this function will be a constant. It will be 2 to the power number of vertices of h. So it's not even a function, it's a constant function. So they have constant expansion instances. So this f is sometimes called the expansion function. I mentioned it in the tutorial, but I think it's good to remember, so I'll re-mention it again, that it doesn't make sense to talk about whether a graph has bounded expansion or not, or even if a finite graph class has bounded expansion or not. I mean, the answer is trivially yes, because obviously all the minors of this graph class, including the d-shadow minors, will be small. They will be smaller than the largest graph in the class. And so obviously their density will be bounded by that number of vertices. So if you have something finite, whether it's a single graph or just a finite number of graphs, they obviously have constant expansion. So it's not meaningful, and so that's why we usually take infinite graph classes if we want to speak about bounded expansion. So you see, it's not the same as, for example, chromatic number you can define for a single graph, right? But you cannot say, okay, the expansion of this graph is such a number. No, this is really for class. Okay, so another example that was given in the tutorial is graphs of maximum degree delta. So the examples we had h minus 2 graphs. You have graphs of maximum degree delta. This is also a graph class of bounded expansion. Graphs of max degree delta. Just to give a hint on why this is the case, well, if you have your h shallow minor, d shallow minor h of g, so you get this minor model. So these guys have radius at most d. Okay, and this is, let's say this is your h. Okay, but now we know that the initial graph g had bounded maximum degree. So this tells us that this ball here, this branch set, has a bounded size. So it has size how much? Well, at most this. So radius d means that there is a central vertex. We'll always see this picture. There is a central vertex c, right, which reaches everybody at distance d. So since my graph has a bounded maximum degree, so delta. So it has delta neighbors. It has, let's say, delta squared second neighbors, delta cubed third neighbors, and so on. I mean, I'm over-exaggerating. But in total, you have, roughly something like delta to the power d vertices here. And each of them can have how many connections in the outside at most delta. So that means there are at most, here going out, there are something like delta to the d plus 1 edges. Right? So what it means is that this graph h will have maximum degree itself. Maximum degree at most delta to the power d plus 1. And if it has maximum degree at most delta to the power d plus 1, well, it also has average degree at most this, and so the density will be at most delta to the d plus 1. So this shows that a graph class which has a bounded maximum degree will have bounded expansion. Notice, interestingly, that this sign is far from constant. This is actually, when you look at d delta as a constant, this is something exponential. And this is necessary to kind of reduce this. So some graph classes have small expansion function. It can be constant for h manager. It can be even polynomial. But sometimes it requires to be exponential.
Could you please repeat this delta power d plus 1?
Yeah, it will be in the tutorial solution. But basically, you agree that this ball of radius d has at most this many vertices. Right? Because you take all the neighbors, you have delta. Each neighbor has at most itself delta neighbors. You do this d times, so you have delta to the power d. People in that ball, now we are counting the number of edges which go out of that ball, because these are these kind of edges, right? Which connect two branch sets, column sets. So since every vertex here has a degree delta itself, so you just add another factor of delta. So you get delta to the power g plus 1. Okay. But this is exactly an upper bound on the number of edges on the maximum degree here in H itself. So that means H itself, it's not dense. H itself has maximum degree, this much, which is huge, but still bounded. And so that means the density of H, which is this, is bounded, right? Because the number of edges is basically at most maximum degree times V divided by 2. Okay? So that shows that. Graphs of maximum degree delta also have bounded expansion. Okay. So you know, now this picture maybe starts making a bit more sense. So you have excluded minors are here, so this includes all these things. And maximum degree is also here, and they have no extension.
So these lower dense graphs, they have bounded expansion.
No, bounded expansion implies noidence. So noidence is a less restrictive definition because in noidence you want to bound not the average degree, but you want not the edge density, you want to bound the clique number. You may have small clique number, but large average degree. Think of a complete bipolar graph, for example. Clique number is 2, but average degree is very large. Right? So in noidence we allow minors, density minors with large average degree, but we forbid cliques. So that's why noidence are very high in that curve. In fact, they are here in my picture. And so by the way, I mean, we have seen also in the exercises that there is one exercise which says that if you have a graph class of bounded expansion, these graphs are all degenerate. So the degeneracy is essentially f of 0 to f of 0. Right? Because, I mean, basically if you look at the other definition of degeneracy, it is, the minimum degree of every new subgraph must be small. And this tells you that the average degree of every new subgraph is small. And the subgraphs are exactly when you take d equals 0. When you take d equals 0, that means your branch sets are of radius 0, which means they are single vertices, so it's just a subgraph. So you can see this grad function as an extension of the degeneracy. When d equals 0, it essentially means the maximum average degree, which is roughly the same as degeneracy, whichever you prefer to think of. I mean, you have seen that mostly we don't care about the constants, right? The theory will not care about constants, especially today. You will see that there will be constants which are even worse than constants. That we will take functions of each other, and this will be fine for us as long as things are bounded. So another, I think, good example to think about is the subdivisions. Like you know the topological minors, we have seen that last week, I think. If you take, all the, let's say, your class is all the subdivisions, all the one subdivisions of a complete graph. Right. So basically, for 2 it will be this. You just subdivide everything else. Now what you observe is that this graph class does not have bounded expansion, if I'm not mistaken. Right? Why? Because if you take the depth 1 shallow minors, you can do something like that. So if you take depth 1 shallow minors, you will find arbitrarily large cliques. Because in any complete graph, you can essentially swallow these degree 2 vertices. Okay. And what you see is that you get 1 shallow minor, which is essentially a clique. So it means and you can form any clique you want, like that. So the density will be as large as you want in this class. So this will not be bounded even for d equals 1. So this is far from being a bounded expansion. Okay. In fact, it's even far from being noidence, because remember, for noidence I was bounding the clique number. Even here my clique number is not bounded. So So these guys, even though they are too degenerate, they are far from being even no evidence. Okay, but now you can ask yourself, all right, isn't then bounded expansion or no evidence, isn't it the same as forbidding some subdivision of T? Right? Because here I'm allowing large subdivisions of T. But this is not true, and if I am not mistaken, if you take this second class, which is basically something like, let's say, the 2n subdivision of Kn. So now I'm not fixing the number of subdivisions. I'm making it so the bigger my clique, the bigger the number of subdivided vertices. So that means if n is equals to 2, so 2n, so that's like 4, something like that, and then for 3, it will be 6. So I'm subdividing, but the bigger I go, the more I subdivide. Now the intuition is that this makes this function grow. I mean, not this function grow, but the d required to get the clique will grow. This is what I mean. So now if I take I take fixed d. Let's say I know d equals 2. Okay, so for d equals 2, you can see that, well, I can get k2 here, and this guy. But now the best I would choose would be this guy, because he's usually highly connected. It's of course more visible when other complete graph. So I take this as my center. Okay, but because I have subdivided like roughly 2d times, I can only go up to a certain point here, right? So the intuition, I mean, maybe you have to do 2n plus 1 or something, but the intuition is that this will not create a clique, right? Because these balls will be too short. So for every fixed d, maybe this is not the right clique, maybe I have to go one step further, but there will be one clique which I cannot get. So this easily will show that this graph class has no evidence, But in fact, since your graphs are very simple, they're essentially, the minors you get are kind of subgraphs of these kind of subdivided cliques, so in fact, they also will have a bounded density, edge density, if I'm not making a mistake. So this shows that you can allow arbitrarily large subdivision of complete graphs, but you cannot fix that. You have to increase the number of subdivisions the more you grow your cliques, and then this will have bounded expansion. So that basically shows that bounded expansion is not the same as forbidding topological minors. In fact, if you forbid the topological minor, you are bounded expansion. I mean, it's not trivial to see it, but this is true, but the reverse is not true. With this diagram is here. Minor is certainly true that we have seen yesterday, Shapley gave a proof, but even topological minor or excluding a subdivision is the same thing. This also has bounded expansion. But this is not trivial, but actually I will maybe show you why. But let me give before. No, let's do it now because I just mentioned it. So this definition is not that important. I'm just mentioning because it's kind of useful in the theory because many people use it in the proofs. But it's just a small side remark that you can define shallow topological minors. And the definition is very intuitive. It is the same as, it's similar as the normal shallow minors, but you take subdivisions instead of. Right? So what you take is, let's say, topological minors. So that means your branch sets actually should look like this. So it should give you a subdivision, right? So it means that this is essentially a subdivided star. So it's a specific, like topological minor, you can see as a specific way to make a minor. It is more constrained. You are not allowed to branch, actually. I mean, it's called branch set, but in this case, you're not allowed to branch. You have to just take a star and subdivide, because it should be a subdivision, right? So this is a topological minor model of depth d in the sense that here the radius is at least d. So it's the same definition, but so now you can define, what they call the top grad. They denote it like this. Top for topological. Of G, which is the same thing, the maximum edge density of a topological minor of your graph.
Top grad is for topological.
Yes. Topological minor of depth. So, this is not very important if you skip following that, but just telling it for completeness. Because I might mention these things from time to time. I will never use it, but I will mention that, okay, this proof is obtained via this or something. So H is a topological minor. Okay, and then okay, now you could define topological long expansion. Right? Same thing, you would just say, oh, I want that my top grad is bounded. But this is not useful, because these things coincide. So there is this result, which says that.
What is the difference between D shallow minor and D shallow topological minor?
So topological, you understood the difference between minor and topological minor? Minor, you contract. That's a very good question. When you do a minor, you can see it like this, that you want to create your H, where the vertices of H will be these branch sets. And then there will be edges between the branch set, modeling the edges of H. It's an equivalent definition that Jackie has given many times, 2 or 3 times, for minors. Okay, but in minor you can do this kind of thing, right? You can really branch. In fact, you can have a minor where, any large minor where the graph has maximum degree 3, for example, by doing this kind of binary tree construction. This is fine, as long as this is connected. In topological minor, you want a subdivision. You don't want a minor. So what is a subdivision? Is you want, so let's say, so you really want this graph. As a subgraph, you want a subdivided copy of H. Now observe that you really need the minimum degree to be at least that one of your H. Sorry, maximum degree. Because now you're only subdividing, so you cannot reduce, like here, there is a trick that when you contract this becomes high degree. But if you subdivide only, you needed high degree in the first place. So this is a more restricted version. So that's why I said subdivided stars. Right? Because since you want a subdivision, these are your original vertices. Okay? So H, let's say, was this. So now, what is this viewpoint? Well, you just take these things as the branch sets. So that there is just an edge here. Right? And every branch set should basically contain a subdivided star.
So we are subdividing the graph? Or
so you take your graph G, you want to find inside your graph G a subdivided copy of H. So this is G. I'm not subdividing G, but I want to see my H as a subdivided copy of G. This is what it means to be a subdivision. H is a subdivision of G. We also sometimes call it that H is a topological minor. So it is kind of a strengthening of these minors. So minors are a bit more flexible because of this idea that, yeah, you can do anything with max degree 3. You just need connectivity. Here, you not just need connectivity, you need this star. Of course, there could be more edges. That is allowed, but it should contain this star. So this, by the way, shows that we had this example in the tutorial, right, last week, that the Peterson graph cannot contain K5 as a topological minor, just because it has maximum degree 3, and you will need vertices of degree 4 to get K5. And if you subdivide, you still keep degree 4. So in Peterson graph, you have degree 3, so it's cubic, so you can't get K5 as a topological minor, but you can get as a minor because you can contract. Okay. So, you know, for normal, for unrestricted radius, it means that these two notions are very different, okay, because of what I just said. But when you are a little bit loose on this, so when you restrict the depth, and you don't require the same depth, actually they become equivalent in some sense. So I'll show this theorem statement. So this is this side is follows from the definition, because every topological minor being a minor, every density topological minor being a density minor. Whatever you can do topologically, you can also do with normal contractions. But there is another side of this, and then this shows that I think it was something like this. This is true for every G. So essentially, you can bound, even this can be bounded by a function of the other. So actually, I was wrong, it's even for the same value of t. So this is the theorem by Jack. I think, what is it, 2007?
So every
This is d squared. So for every d, every graph G, and every d, essentially, I mean, this is not very important, and the precise values are not important. What is important is that to see that this colleague, Zolciak, who has worked a lot on these notions from Czech Republic, he showed that these things are essentially bounded by each other.
So can you repeat what's written there?
Sorry?
4 times
This is 4 times 4. I mean, I'm not sure about the constants. 4, 4. This is just this.
This is 16 times. So it's 16 times, right?
Well, I mean,
D squared is outside?
yeah, it's no problem with the corresponding. I don't remember that.
Then write C.
Oh, probably it's like this. I think it's this. Anyway, that is not important. The important thing is that this is some function of there. Each of them is a function of each other. So what it means is that, well, see, for a bounded expansion, we are only caring about some function, right? So if one of them is bounded by some function, I mean the other one is also bounded by some other function. Slightly more complicated function they implement. What it means is that if you define classes of topological bounded expansion, it will give you the same theory, right? But what is the reason why I'm mentioning? I mean, first of all, it's nice to go back to these topological minors, but yeah, this is actually useful in many proofs. So in many proofs, what they do, it's kind of easier to deal with these subdivisions. So they actually use this, and they show that, oh, this is bounded, or so the other one is also bounded, something like that. I will never do this, but sometimes I'll mention, this is proof using that technique. So it makes it, apparently it makes it much easier. Okay. All right, so this was just a side remark. Let me mention some other examples of graph classes of bounded expansion. This is also a little bit proof, just kind of for your filter to see that there are nice things along there. Other examples. So one example we gave in the tutorial, which was so many of them actually come from this graph drawing. you want to draw your graph in the plane or something. So these k-planar graphs, they have bounded expansion. So what it means is that means you can draw them in the plane, but something happens like this, that you bound the number of crossings. So every edge is crossed at most k times. Okay, so these are bounded expansion.
Every edge is crossed at most k times or only at most k crossings?
No, every edge is crossed at most k times. This is different from the crossing. There is something called the crossing number, which is the smallest number, so that number of crossings in a drawing in the plane. This is different. In some sense, in fact, this can be generalized. It's a beautiful theorem, I think. Because you can, what can you say? You can say that, okay, for every edge, and make a new graph, say H from G. This is G. And now, what I'll do, I will make an edge if they cross. I will draw an edge between two edges if in the original graph they cross. Okay, so this was E1, E2, E4, E5, E6, and I'll get a graph with 6 vertices. It's a little bit like the line graph, but it's not the same. So E1 crosses E2, E3, E4. Okay, so my crossing graph looks like this. Let's make it a bit more complicated maybe. So E7, E7 also crosses these guys. This is, I can define my crossing graph. And now there is a nice theorem which generalizes this. So this is by Epstein and Sidal Gupta, who is a colleague of Bitskoa, some of you might know. So they proved that if this blue graph is, I mean, it's not very formal what I'm saying, but if this blue graph has, if the degeneracy of this f of h of g is at most some function, some constant, then, well, the class of graphs C, well, let's define like this. You take the class of graph C, which is all the graphs which can be drawn such that the degeneracy of the blue graph is bounded. It's a bit complicated, but essentially it means that your crossing graph is kind of sparse. Then this class is bounded expansion. CD. With degeneracy of H of G. In fact, has polynomial expansion. The details are not important. I just want to give you an example. Why this generalizes the k-planar graphs? Because the k-planar graphs were essentially saying that the maximum degree of the blue graph is k. Right? Because every edge has at most k neighbors in the blue graph. So they generalize this by saying, oh, the maximum average degree also works. You take the degeneracy. Okay. And the motivation was actually interesting. If you look at, there is a nice blog post by David Epstein on this. He has a very nice picture of these road networks in real life, right? Especially in the US, in America. So they have these exchanges between highways, and basically on these highways, this number of crossings is unbounded because you have these huge interchanges, and then you have many highways crossing. And they saw that this is actually quite high. But when they draw this blue graph, they checked many cities in the world, and they saw that, oh, the degeneracy is actually small of this blue graph. And then they proved that these guys have small polynomial expansion. So I think this was a nice paper, motivated by some real life application. So sometimes we say, road networks are planar. I mean, this is far from true because we have tunnels orthogonals, we have bridges and so on. When you look at these kind of pictures, they are really impressive. But in some sense, they are still sparse. There is another class of graphs, which it's called the book thickness of the graph, which is this. You have to find an ordering of your vertices V1 to Vn, and you want to draw them on a book. What does it mean? So this is what do you call that? This part of the book. Okay. And now on every page you can draw something planar. Right? So you can do something like that. That should be planar. But now you can have many pages. So some of the edges you will.
No, maybe you can use another color for the second page.
Here is another page, right? And here you can have another planar drawing. Sorry, this is not planar.
But all the vertices lie on that
Spine.
Yes, the vertices on the spine, and now for every page you can draw some edges, but every page should be planar. So the smallest number of pages is the thickness. Page.
I have a small comment.
Sorry?
So I have a comment.
Yes.
So there are similar things which are called Earth-Moon graphs. It's like if people make colonies in moon,
Yeah.
then there will be a different set of adjacency between the countries.
Okay.
And together it will be like two planar graphs,
Yes.
merged together.
Merged together. Yeah.
It's an open problem to find its chromatic number.
Yeah. So this is a special case of that.
No, I think it's a bit different.
Different?
Yeah.
No, because each page can be a different planet, no?
Yes, but the vertices are not fixed on the spine.
Yeah, that's why I'm saying it's a special case.
Okay.
It's a these in particular are like 3 planets,
Yeah.
but it's a special way of doing it, so it's more restricted.
Right.
So this is called the book thickness, and if you have, or maybe this has another number, I think.
How is this drawn? I didn't get this part.
So on every page, you draw edges as you want, but every page should be planar. You put your vertices on the spine, and now you can put edges in any page you want. So the graph might be non-planar, but every edge should give a planar drawing.
So now there are
Let's say
images in the plane, so within each page,
Yeah.
and also from this to another.
No, each page is separate. Each page is
How is the thickness or
Sorry?
what is this thickness?
The smallest number of pages.
Most number of pages.
Yes. Yes, of course you can, if you put one edge for every page, you can draw every graph like that, right? But you have many, many pages. You want to have small pages, like 3 pages, 4 pages, 5 pages, something like that.
It's also a book number of
I'm not completely, I don't know. I think it's called book thickness.
It's called thickness.
Yes.
Book thickness.
There is another equivalent definition, which is, I think, stack number or queue number, there are things like that.
Something like that.
I don't remember which one.
Similar concepts are there.
Yeah, other concepts are there. So there's a whole community of these graph drawing community where they like to draw graphs and they come up with these kind of things. It's quite nice. In fact, Epstein and Gupta are working in this area, among
How
others.
are these 3 colors?
Sorry?
How is this 3 colors?
3 planar? No. There are 3 pages.
Yeah.
So book thickness is at most 3. It's not planar. Every page is planar. If you take the edges of a page, it should give a planar drawing. And special one because the ordering of these on this spine should be the same for every page.
So you can also think of it as partitioning a graph, edge partitioning a graph into planar graphs.
Yeah. This is a more general version. This is more restricted since you are fixing the embedding in some sense of the vertices. But okay, if the book thickness is, so if you take the graph class, so the class of graphs of book thickness K, has bounded expansions. This is another classic example. I can't prove you why, but you can find this in the video. Well, this is just to give you some nice examples.
planar graphs may not have
graphs have boundary expansion since they are K5 minor 3. Okay. So K5 minor 3 graphs, as we saw yesterday, have expansion function at most 2 to the power 5. Okay. So planar graphs has very much bounded expansion. Okay, so we have bounded expansion.
Constant.
Okay, so you have bounded topological minors. Maybe we can draw this something more messy but more explicit picture as this. The bounded graphs, classes of which have bounded topological minors. Forbidden topological minors. Forbidden minor. This includes planar graphs, of course. This includes bounded treewidth, by the way. What did we see? We saw bounded max degree. So bounded max degree also have forbidden topological minors. Because if you have maximum degree D, you cannot have KD plus 1 as a topological minor. So max, so the bounded max degree. And the things I just mentioned.
Boundary max degree and planar, they are disjoint?
No. Oh, it's just this picture gets messier and messier if you want to do all this. So this diagram is maybe not as explicit because here you can really see the inclusions right away, but it's essentially this diagram where the graph class which is below is included in one which is above. Okay, so this is the picture to keep in mind what means bounded expansion. And then of course you have more dense. Which is here. Which is bigger. And there is degeneracy. Bounded degeneracy. So bounded expansion are both Noah dense and bounded degeneracy, but Noah dense are not necessarily bounded degeneracy and vice versa. So that's kind of the big picture of this there. All right, now let's move to today's topic. Which is the generalized coloring numbers. Okay, what makes this theory of bounded expansion very beautiful is that it's very robust and in the sense that there are many equivalent definitions. And what people have come up is equivalent characterizations of bounded expansion classes. And then you can, using this, it can give rise to many applications. Why? Because you may take one characterization for this kind of applications, let's say algorithms, one characterization for, let's say, coloring problems, and so on and so on. So, yeah. So the different types of characterizations is, well, we have these orderings, so generalized coloring numbers. This will be the one we are seeing today, and in fact, I think this is the richest one in the sense that it's maybe the easiest, and you can derive all the other ones using this one. I mean, they're all equivalent anyway, but I think this is, they have nice proofs. It's historically not the first one. Historically, I think it was the bounded, you remember bounded layered, this treewidth that Hamilton was explaining last week, but when you take planar graphs, you can decompose it into essentially graphs of a small treewidth. So this is another characterization of bounded. This is also true for bounded expansion. I mean, some version of that is true. So historically, I think this was the first characterization. And then Zhu came up with this coloring, and he proved that this characterization is there. And nowadays there are even others. So I'll show, let's say, at least 2 and mention 3, hopefully. I mean, I will not show the full characterization, but some ideas at least. All right, let's move on to the generalized colors. Maybe I can keep this diagram for a while. Still some space here. I wish I was able to partition the board nicely as Shagnik is doing. handwriting is not as controlled, I guess. Okay. Okay, so everything comes from this degeneracy orderings. So we have seen yesterday that one of the definitions of degeneracy is that you take an ordering and you look at the backwards degree. The maximum of this, let's say it's the degeneracy of the ordering and the degeneracy of your graph. Among all the possible orderings, is the one which gives you the smallest backwards or left degree. Okay, we are going to generalize this now for other values of d. So in some sense you can say that this backwards degree is a path of length d, of length 1, sorry. Now we are generalizing this, not exactly like that, I will define, but using path of length at most d. And this will give us the correspondence with this d, which is important for this d shadow minus. So at the first it will just be definitions. Where's the best place? Okay, so, oh yeah, and coloring number comes from this terminology. So let's erase this. So we take an, okay, so definition was coined by Courcelle and GIAN. In 2003. But by the way, historically, I mean, the motivation of this was gains. So Courcelle and GIAN, Courcelle especially, they have worked a lot on these games on graphs, and especially these game chromatic number, where you have two players and they try to color the graph. Let's say there are k colors, so Alice tries to color the graph with k colors, and Bob tries to avoid that. So they have to color a vertex at each step. And if Alice has a strategy, this gives you a small, let's say, hopefully small chromatic number, game chromatic number, and so on. So inherently, these games, they give you an ordering, right? Because Alice plays first, then Bob, then Alice, then Bob, etc. So it gives you an ordering of the vertices. So this is the initial motivation of this. If you look at the papers from that time, around 20 years ago, they usually speak about these game chromatic number, game coloring. So as you have seen last week, we have seen the cops and robber game. I guess graph theory is really like games. And while playing games, they come up with beautiful theories, but it's like a side effect. Alright. So you have this ordering. So let's fix an ordering. We have graph G, and I also fix an integer G, and I'm fixing some ordering, sigma. This is sigma. Okay, so let's make a picture. My graph looks like this. This is Vn, V1. Okay, and I'll say that take some Vi and some Vj. So Vi, so for I is at most j, we say that Vi is strongly de-reachable from Vj. What is important here is that Vi is to the left of Vj. So it's like the degeneracy we are looking to the left. What does it mean? It means that there should be a path of length d, at most d, but this path is very special. I cannot take any path that would just give me, the neighborhood of radius d. I'm only allowed to go right once, and then only jump to Vi. This is what I call strongly de-reachable. Vi is strongly de-reachable from Vj if there exists a path from Vi to Vj, the path P, from Vi to Vj, such that all the internal vertices are to the right of Vj. All internal vertices of P let's write like this. This will be, well, all of this, you might think it's the number of vertices, so let's say the length of P. This is the length. Length meaning the number of edges. Okay, so this is called strong reachability, D reachability. You see it's a bit strange, but observe that if you take D equals to 1, it has to be a left neighbor, right? Because the paths are close. So it generalizes this degeneracy business. And there's an, so this is sometimes called just reachability, but there is also weak reachability, so I think it's more explicit if we say strong and weak rather than nothing and weak. Makes it more explicit. And we say that, again, I is at most j. We say Vi is weakly D reachable from Dj. If there exists a path, it's almost the same definition, so that it's going to be a little bit confusing. The path P, but they are quite different. D, so the length of P again is at most D, and all internal vertices. This time they will be to the right of I, not J. All internal vertices of P are to the right with respect to sigma of Vn. Let's do a similar picture. Now I'm less so every time I cannot use this part of the graph. So this Vi is always the minimum of the path. But now I can just do this. Okay, so by the way, well, I didn't count the D equals 9. And here we have maybe it was a little bit too many edges. So this is called weakly reachable. Weak and strong is quite natural because obviously this is a stronger condition than the weak one. I mean, if you are strongly reachable, you're also weakly reachable. It's quite immediate from the definition in the picture.
Again, the length should be at most.
Length should be at most. Length of P is at most.
Okay.
Alright. So, I mean, at the moment you don't see why we're doing this, I suppose, but there will be some applications.
I didn't understand strongly and
See, this path here, you see that between Vi and Dj there is nothing. That means it's strong.
okay.
Here you allow anything between Vi and Dj. It's weak. So it always has to be to the right of Vi. Vi must be the smallest. But here you're even forbidding everything between Vi and Dj. This is illegal. Now, the important thing is exactly like in degeneracy, we are going to count the number of guys which are reachable for every D. And this will be what we call the generalized coloring.
Sorry, what are we going to count?
I'm going to count for every vertex how many vertices are D reachable from it. And my goal will be to bound this number. And, okay, just to give you a these things are for. But for that, we need some terminology, to be a bit more formal. And so there will be some other definitions, which are very natural, but we'll say that S reach for strong reachability, G sigma and Bj, it's essentially the set. It's all the Vi. Vi is strongly reachable from Vj. Sorry, it's the set. And W reach has the same definition with W. Sorry, there is a little d, I might forget that from time to time, but this is actually important. So we have 4 parameters like the graph, the ordering, the vertex, and the d. This is the set of VI's, such that VI is weakly reachable. Reachable from Vj. Observe that, for example, in this picture, all the guys which are here, so remember that VI must be smaller than Vj. This is important. Think of the degeneracy as a motivation. You always look at the left. But of course, now you're allowed to use the right side. But the ones you are counting are the ones on the left. So all these guys are also weakly reachable. But here, if you look at this path, only this is weakly reachable. Obviously, I will have more if I draw a real graph. So maybe I can give an example while you digest the definition. Okay, if I look at my DJ. So what is the strong reachability set? Well, for d equals 1, these two things coincide with the degeneracy. So it will just be the set of neighbors on the left side, but let's say d equals 2, it becomes more interesting. The weak reachability of set of Vj, I will just abbreviate, like, to avoid writing G sigma or G sigma clear, I will just write like this. I hope you forgive me. Okay, so who is reachable? Strongly, I said weak reachable from d equals 2, so, well, of course you have this guy, you can go up to 2, but now you can also go here. So, this actually himself is also. So you're always, yourself, you're always d-reachable because there is a path of length 0. And I is at most j, not strictly. So.
3 of them, no? That is also distributed. The third one from the left.
Oh yes. Yeah. 4. So there is 4. Okay, this is W push. There are 4. Itself is also good.
You want paths of length at most 2, right?
Sorry?
So you're looking at all paths of length at most 2, right?
1, 2. 1, 2.
So then there are all paths of length 1. Like if you just go to the vertex.
This. So that's why I have 4.
No, isn't there a small path right next to the vertex next to it?
Here?
Yeah,
Yeah.
less than equal to d.
No, there is no path here.
There's no path.
Oh. So consecutive vertices might be non-adjacent.
Okay.
There is no, it's not a path. The graph is not Hamiltonian. We are just ordering vertices randomly. But of course, you're right. If there was an edge here, this guy would be, of course, in the weak reachability. Okay. What about the strong reachability? Well, obviously it will be a subset. I don't know in this case what it will be. Hopefully, it's a strict subset. Yes, it is because I'm not allowed to use this path for the strong reachability. Remember, I can only go to the right. So for the strong reachability, I take himself. Well, I take this one because it's a distance 1, but I cannot take this one. This is stronger, so it's more difficult to reach. Remember this picture. If you're strongly reachable, you're also weakly reachable. And strong, you're forbidding more things, so it's just more difficult. If you can do the more difficult thing, you can do the easier thing. Usually. In here it is the case. Okay. Alright, and now, well, we need a few more definitions. Sorry about that, but with all these parameters, it's always the case. Unfortunately, my board is full. But where is it? I guess I can go this one first. I think this picture is probably nice enough to keep. Okay. Okay, so we will just say that this will be a bit. I'm just, for the sake of completeness, I will give all the notations, but there are essentially 4 notations. So the strong coloring number for radius d of g sigma. So you're fixing a graph and then ordering. This will be what? Will be the maximum size of the number of reachable vertices. Max for all the b, I, and b of g of the size of the strongly reachable. And similarly, so it's like the degeneracy, right? I want to minimize, but you know I have to count the maximum. That's the worst case. I take the maximum number of reachable. And W equals D, same thing with weak reachability. Okay, and so now I can finally define my. Now I take the mean over all possible orderings to get the coloring numbers. The strong coloring number of G is the mean over all ordering sigma of G of the strongly of G sigma. And recoloring sigma. So I do it this way so that I can have a parameter for a graph. So it's among all possible orderings, I choose the best one. And the best one is the one which gives me the smallest reachability sets. So we'll go on maybe for about 5 minutes and give you a break.
So both these parameters are at least degeneracy, right?
Yes. So in fact, for t equals 1, both of them are equal to the degeneracy plus 1. So the coloring number, essentially. This will be my next. I'll give a few easy observations. So, observations. So, strong coloring number of 1, G equals to weak coloring number of 1, of G equals to the degeneracy of G plus 1. Right, because in both these notions you're only allowed to take path of length 1, so it's neighbors, backwards neighbors. But you're counting yourself, so you get the plus 1. That's why why this is a generalization of this coloring number, which is defined as well. Well, it's not too difficult to see, but these things are monotone, right? Because if you're reachable with the path of length d, well, you're also reachable with at most d plus 1. And in fact, there are some super nice things. Well, this is not observation, this is like a proposition or theorem. I'll not prove these things. But when you don't restrict d, when you take d to be large enough, let's say infinity, to be safe, or the number of vertices of the graph, what happens? The strong coloring number, let's say infinity of g, but you can replace this by the number of vertices. You take the length of the path. And the weak coloring numbers, they are some nice notions. Which so the strong coloring number is more restricted. This is equal to the treewidth of g plus 1. So what we are doing here, given these orderings, is actually equivalent to doing things like trees, treewidth. And the weak coloring number, this is another thing, I mean, I will not define today, but it's called the tree depth. Tree depth is a weaker notion, or stronger notion than tree width. You are restricting your tree decomposition to some very special thing. So when we take 1, we get the degeneracy, and when we get any unbounded radius, we get some nice measures like the tree width. So if we have time at some point, I mean, I put this in the tutorial. It's not too difficult to do. I don't know if I will do it or not in class at some point. I have time, let's see. Not today, at least. Okay, and the initial motivation I was telling you about these games. So if you're interested in that, you can look at this game coloring number. There is the game chromatic number. Things like that. This is called the marking game. This is an upper bound to this one. Well, I'm not going to define this, but this is the initial motivation to do this. And people were studying a lot this acyclic chromatic number. And I think that's how they came to this, Because what's the acyclic chromatic number? It's we take a coloring, but any two color classes should induce a forest. So it's a restriction of the normal proper coloring. So in proper coloring, every color class is an independent set. Now you take two color classes, which should also have some nice property. It should be a forest. Actually, you can see this as any one color class has treewidth 0. Any two color classes have treewidth 1. You can see how this is, where this is going. You could generalize this.
That is a proper coloring with that extra property.
Yeah.
Okay.
There's an extra property. Any two color classes. I mean, I will not use this. Proper coloring. This is a very classic notion in coloring. And at that time, they were using this to bound a lot of things. Also, in these colorings or oriented colorings, things like that Charlotte is studying, they use acyclic chromatic number.
Game coloring number, what have you written inside that? Game coloring number?
No, I'm not defining it, but I'm not defining it, but
What have you written on the board?
marking game. So there is something called the marking game, where Edison both marks and vertices. I'm not going to do that. any two color classes induce a forest. Okay. Well, what the important thing is that what they observed is that the strong coloring number of G, well, and that's 2, bounds the acyclic momentum. So that was very useful to them. Well, to the first one. This is not too difficult to observe, by the way. If you're interested in these things, you can look it up. I'm not going to show it. Another 45 minutes. So I'll just say 2 things. 2 results I'll just state, and then I'll show you a proof after the break. So one thing is that, well, okay, another thing I forgot. In the observation, I should have said that the stronger coloring number is at most the weak coloring number. Let me add it. So this is clear because the strong reachable set are included in the weak reachable sets. You will get less. The size will be less for the strong version. But actually the reverse is more like, not the reverse, but approximately true. And I'll try to prove this after the break. So we have that the weak coloring number. Oh, okay. This is the same thing. This is like almost by definition. But this is at most. So what's the exact value? 1 plus d times g. So some function. So the weak coloring number is at most some function of the strong coloring number. This is also true. ND. So this is 1 plus d times strong coloring number minus 1. So what it means is that if you fix your d and you're not worried too much about constants, or even polynomials, because you're taking this to the power d, then like if one is constant, the other is constant. And this will be really nice because it means we'll be able to work with either of them. In fact, in practice, the weak coloring number is the one which is used to prove things. But then the strong one is important, well, for lower bounds, you can use it. So it depends on what side you're doing. And actually, well, these things can be computed also, not necessarily exactly, but there are approximate algorithms for this. But okay, before the break, I want to show you why we are doing the whole thing. This is a theorem of Zhu, 2009. So the following are equivalent. Let's see the graph first. your weak coloring numbers are bounded, and your strong coloring numbers are bounded. So I'm going to take this. There's just the first function, f1. Okay. Such that for every g in your class, for every d in your natural numbers, the weak coloring number is bounded. And the third is the same with this strong coloring. That means that using these coloring numbers, we actually get characterization of graph classes of boundary expansion. Okay. Let's take a break. 5 minutes. I'm going to adjust this a little bit. told you that so Ling Zhu, who is a Chinese researcher, very famous in graph coloring and things like that, proved in 2009. So he actually worked a lot on these grain chromatic numbers. I think he still has the best bound for the grain chromatic number of planar graphs. It's like at most at 17 or 16 or something. So, but then he also worked on this bounded expansion, and he showed this equivalence that passes bounded expansion if and only if both of these generalized coloring numbers are bounded for every d. So that they are bounded among each other, this follows from this proposition, which I will try to show now. This being trivial, but I will try to show the other one. And okay, what I can show, I don't know if I will have time either today or either this morning or this afternoon. In the second lecture, I will show that if your coloring number is bounded, then you have bounded expansion. That side I will show you, and the other side I will not show you, it's more complicated. And it uses the topological proof. The proof which I've seen uses the topological one. I don't want to go into that in details. It will be too long. So let's prove this. Definition. This follows from the definition. Right? Because the strong reachability is always smaller than the set.
So these are, we should call them numbers.
Yes. This is a number. So this is the, okay, so yeah. Remember what this was? You're looking at all the possible orderings of your product set. You're looking at these reachability sets. You're looking at the maximum you get, but you take the minimum of all possible orders. When you take a fixed ordering, you are forced to get the maximum reachability set, but you try to optimize using a different orderings. This is the which ordering. Think of it really like the degeneracy. Degeneracy for a given order is like you take the maximum number of backwards neighbors, but you're trying to find the best ordering. It's the minimum of the max. It's a min-max parameter. So what we're going to do, we are going to observe, we are proving this for every sigma. So if we prove it for every sigma, sigma being an ordering, it will be also proved for the optimum one. So we fix the sigma, v1 to the end, and we are going to take some vertex, and we are going to prove that the strong reachability of this vertex, okay, yes, so I'm going to observe the strong reachability, and I will deduce something about the weak reachability set of the same vertex. So consider the strong reachability of for some d for that particular sigma and for some vi. And I will call this k. Let's say that S covering d of g is k. Okay, and so I take it back, I don't take any ordering. I will take the one which gives me the best strong covering. Okay, I can do that. Okay, so I take the reachability set of some vi. Remember the picture? I have my vi. What does it mean? It means that I can use half which go like this, and then they go here. say that this will not be too big. Now look at the weak one.
I have a question. So,
Yes.
in this diagram, what are we reaching for? So, you said that when you define something that the jump is always towards the right, but here we are moving towards V1.
I jump d minus times up to d minus time to the right, and the last jump is to the left. Remember, I say that Vj is reachable if it is only to the left. But in strong reachability, I jump to the right, and the last jump goes to the left. In weak reachability is less restrictive. I can jump anyhow I want, even to the left, to reach. Okay. But this path, this P must have length at most. Okay. This is the. So here we have S1, S2, S5, and every path here on EI, Sj, the length is, all these paths have length at most. This is the definition. And because the strong coding number of G is K, and I'm taking that sigma, which works well, I can assume that my reachability set has size at most. For every VI. Why? Because this K is the maximum. For sigma, I'm taking the maximum size of the reachability, so all the reachability sets have size at most.
K.
K, sorry. But what we are really interested in is the weak reachability set. And we want to upper bound this by some K, function of K. Okay. Just behind. Okay. What I want is I want to show that this set, let's go to W. Size of Wy should be at most what? K minus 1 to 1 plus D, K minus 1 to the power D. Right? K is my strong reachability set. Okay. So what I'm doing, I mean, if this weak reachability is also happens to be by chance strong reachability, I'm good, because then I will know it's at most K. But the trouble is these things. Right? I can use these in many ways. Right? Into another vertex, and they are giving me trouble. So I have to take care of these guys. What I'll do, I'll just focus on one of these paths. And they shouldn't move. Anyway, we'll focus on the pink one. So what I will do, I will look at the jumps, which I'm doing here. So what happens? I'm jumping to this vertex. This is the first. Then I'm going here, second, third, fourth, fifth, and finally sixth. Let's say D is 6. So this is the ordering on my path. It doesn't have anything to do with the ordering sigma. It's just how I traverse my path. So I will call a milestone. These are the vertices of P. Okay, let's say this is J of P, such that Vj is minimum of sigma over the self-path when I start at EI and I arrive to Vj. Let me explain on the example. So at the first, my path starts at the smallest guy I have visited so far in the ordering on the path. And I'm going here, here's not a milestone. Everything on the right will never be a milestone because I've already visited this one. Not a milestone. But this is a milestone because on the subpath of size 3 here, of 3 vertices, he is the smallest one so far visited. So he is a milestone. He was a milestone. Now I'm going here, he's not a milestone, because again he's not the minimum. But this guy is a milestone. I'm going back, not a milestone, and the last one is always also a milestone, because he is, by definition, he is the smallest one. Definition of weak reachability is that we don't use anything to the left of J. So these are my milestones. So what I want to do is say something about these guys. Well, what I want to say about these guys is that let's give them numbers. This is W1, N1, the milestone, N2, N3, and N4. I have 4 milestones. Okay, so there are like N1, F2, and whatever, T. I don't know that number. These are my milestones.
So that is Vj of t. So that Vj is minimum.
Sorry?
Vj is minimum.
DJ the vertex index.
Where is VJ?
Milestone vertex Vj
Of
of
P? Yeah, so sorry. P vertices of.
Vj of t. Like J is higher or I is higher?
Yeah, so I is higher. So Vj is minimum. So I'm taking here, my milestones are this Vj, so this Vj, because it is, Vj is Vi at this time. Now I'm having this guy is Vj, and he is minimum on the path from Vi to Vj. This is not, because when I take the path from Vi to Vj, he is not minimum, this is minimum, so he's not. Now he is, yes, so this is my Vj at this stage also. So it's all the Vj's which are minimum over sigma. Is it not?
What do you mean minimum?
On sigma, for the sigma, minimum in the ordering. We have an ordering, right? This is the smallest, this is the biggest. I'm always so for when I say minimum, I take this ordering. So I'm building my path, right? Imagine you are building your path little by little. You start here. So at this moment, the path has just one vertex. Obviously, that vertex is minimum for sigma among all the vertices in that path, right? This is minimum for sigma over that path. I mean, on the along maybe among the vertices of that path. This is here. Yes. Oh, because the strong reachability sets are smaller than the weak reachability sets.
So it's strong maximum coloring number is at least the weak coloring number, right?
At most, because I'm counting the size of the reachability sets. If the strong ones are always included in the weak ones. It's not possible that strong one is bigger. Strong one is smaller. Because you are included, the reachability set is always included. The strong reachability set is a subset of the weak. So since I'm counting the size of the weak reachability sets, yeah, so the strong is always the size, since it's completely included in the weak, of course its size is small. For every vertex, in every order. Is it not clear, sir? No. So see, I'm building this path, right? I start at my VI. Path at the beginning, so I'm only considering vertices of the beginning of the path. I'm checking if this is minimum. This is now minimum, because among all the vertices of this path, which has just size 1, of course this one is the smallest, there is only one. I'm considering this ordering, right? From left to right. This is 1, 2, whatever, the end. The smallest. Now I'm going to the right. There could be many more vertices here. I'm just looking at the pink ones. Who is smallest? This one. He's not smallest, so I'm not taking him. He's biggest. So now I'm going back. Now, on this path, who is the smallest? This one. So he is a milestone. So this is N1. This is N2. Now I was going where to the right? Not smallest. It's not the milestone. Smallest, N3. Blah, blah, blah. And at some point, point I reach my Vj, and he obviously will be the last node. He's the smallest in this path, in total. So these are my milestones. Now, the crucial observation is that if you take two consecutive milestones, so m I plus 1 belongs to the strong reachability of the previous one. Is this true? It's not difficult to see if you got the definition of the milestones.
Are we calculating the milestones for each vertex, or is it like a
Path or a vertex?
No, for a path.
for the path?
So you take this Vi, in fact for every pair Vi Vj, where Vj is in the weak reachability set of Vi, we are looking at this one witness path, and we are looking at the milestones. So the idea is that I will try to count the milestones will be used to give some kind of signature of that path, and I will show that the number of signatures is bounded, which will tell me that the number of possible pairs is bounded, and which will give me an upper bound on the weak reachability. This is the main idea what we're trying to do. And the way to bound it is using the strong reachability, because that we know it is small, it is k. So I'm claiming that if I take two consecutive milestones, the next one is strong reachable, named D, from the previous one. I think it's not too difficult to convince yourself if you look at the picture. So of course all these guys here, they are never milestones, because this is minimum. That's good, because they cannot be in the strong reachability set. Okay. So you see that the next milestone is in the strong reachability. Why? Because I'm going to the right, and then since he is minimum for the things I have seen so far, that means there was, and he was also minimum previously, so that means there is nothing in between, basically. That's the argument which says it is in the strong reachability. If you look at the two next ones, you will have the same property. This was M3. Okay, I visit this guy, but since the next one is this, I have not seen any one in between, because otherwise he would have been the next milestone. So this tells me this. So that means how many milestones are there? Well, at most k, because, sorry, not at most k, but it's not like that. It's more that.
So if M3 and M4 are milestone, can I have a path from M3 and M4? Can they be neighbors?
Yeah, they can be neighbors. Sorry, M3 and M4?
Are milestones. Then can M3 and M4 be neighbors?
They can be. In fact, instead of jumping like this, I could have jumped immediately like this. So imagine I could have been like this.
So what do you mean by this minimum? Minimum for sigma amongst V. So
Among the path, so you're looking at the path, the prefix of the path. So at this stage I'm not considering this guy because the prefix ends here. And this guy should be minimum over this ordering, so it should be the leftmost possible. On that prefix of the path. Of some path. I'm considering one path. Maybe that wasn't clear. I'm just considering one of the paths, which is witnessing my weak reachability.
So I have many paths of length D.
Yes.
Any one of them, and the first vertex in that path is that milestone.
Not exactly. So you fix VI, you look at Vj, which is in the weak reachability. Since it's in the weak reachability, there is a path of length at most D. And on this path, there will be many milestones. And the milestones are kind of iteratively the smallest I'm visiting. So first I'm going here, it's not a milestone because it's not smallest. Then I'm going here, he was the smallest, he becomes a milestone. If I'm going to the right again, it will never be a milestone again. So everything which is to the right of this will never become a milestone anymore because it will be bigger than this. But each time I go a little bit to the left, he becomes the new milestone. I might go a lot to the right, but that's not important. The first time I go to the left, it is the next milestone.
So now I go right and again come back, that becomes milestone.
Yes. If you go to the left of the last milestone. So each time you visit something more left than the last milestone, you become the new milestone. Maybe this is clear.
everything towards the left of VI is a milestone.
No, because you could jump first here before you move.
Okay.
Exactly this was happening actually. In my previous example, it was like this. So I was first jumping here. This was a milestone and this was not a milestone because I wasn't there first. So not everything is milestone. But this is there. Okay, so now, what we do? So to Vj, I associate some kind of signature. Let's say actually the pair Vi Vj. So Vi is any vertex, and Vj is in the weak reachability. Wi, call it Wi. I assign a signature. What is the signature? Well, it's the choice of the milestones. So this path P, essentially you can view it as a sequence of milestones. And since the path has at most length d, there are at most d plus 1 milestones. So the length is d, so there could be d plus 1 for instance. Signature, which is the sequence of at most d plus 1 milestones on P. On P, which is a witness of V1 to Vj. Saying that Vj is in W1. Okay. So you know there is such a P and you are just looking at the sequence of milestones.
So the signature is for a path.
Well, I'm choosing one path. It's for a pair of vertices Vi, Vj. I know there is one path. I take, maybe there are many, but I take one.
Okay.
And
Anyone.
Anyone, and I'm saying this is my signature. What I want to do is count the number of signatures and show that this is bounded anyway. So even if you have multiple paths, since the total number of of signatures is bounded, I will have a bound on my assisted ball. Okay. Right, but okay, these milestones, they are themselves. So consecutive ones were each in the strong reachability of the previous one. So it means what you're doing is okay, the first milestone is always V1. So how many signatures? That is the question. How many Vi, Vj signatures for fixed Vi? This is my question. Okay, but this corresponds now to the first, I always take V1 as my first milestone. Okay, and then the next milestone is in the reachability of V, strong reachability of V. So I have k choices for the next one. Because strong reachability is always at most k. So you see here, I kind of iteratively will use the strong reachability argument to bound the reachability. So Vi then k choices for, so this is M1, k choices for M2, and then k choices for M3, etc. And there are at most d hops like that. So d choices are done. D at most d. I mean there are d plus 1 milestones, but at most d. The first one is always Vi. And for each of them, I can choose, so this is k times k times k times k choices, k to the d. Right? You see this k to the d here. Okay. So number of signatures for Vi. At most. Technically we could have just one milestone, we could have we don't know the length of the path. The length could be at length 1 or 2 or 3 up to d, so it's technically it's like if you have just one milestone, it's like k plus k squared. If you have 2 milestone plus k cubed. So it's like sum of x equals 1 to d. The maximum number of choices will be d. Of tends to the d. The signature will be this. Okay, well, actually it's plus 1 because it could be that reachability is just successful.
Yeah.
What is this, sorry? What is this? K to the s. K is that strong reachability. It's the same K, isn't it? Okay, and this is basically that moves this kind of functions. This is like d times k to at most d times k to the d. Where do I get the minus 1 there? I don't know. Maybe we can squeeze out minus 1. I don't know where it is. Okay, but the completion of the argument is that I was looking at the pairs, the signatures from a guy VI to a VJ, which is in its weak reachability set. To each of them, I'm associating a signature. And I'm counting the number of signatures, and I'm saying that there are not too many, there are that many signatures. Okay. But if two vertices have the same signature, that means they have exactly the same milestones, and in particular, they have the same vertex. So if you have a same signature, you are actually the same vertex, because the last milestone is this VJ. So if you have the same signature, you're the same. So any two different ones must receive a different signature. But that's the maximum number of signatures. So the conclusion is that this is another one. Conclusion. The weak reachability G sigma VI is at most this number.
I should pick k minus 1 choices because we are already excluding m, like vi is m1, right? At each step itself is getting excluded.
Yeah, but that's why I only went to D and not to D plus 1.
Not in the
not that.
in the strong color D.
Yeah.
Yeah, we are
Ah,
including,
yes.
Besides this
Correct,
that
correct.
we
yeah,
are
we are including that vertex.
Correct. So what you're saying is I could have done this.
Yes.
Yes, correct. Yes, because in the strong coloring, vertex VI is itself there. But I'm not. VI is always the first milestone, so I'll never. Sorry, VI is always the current milestone, and we are going from milestone to milestone. MI is already, so yeah, correct. So we can get this milestone. Thank you. Okay. So I think this is a nice illustration how to use these things. I mean, here obviously we are just proving a bounds for the sake of the bounds to see that they're together. But when we will see applications, the philosophy of the proofs will be the same. So we will sometimes use an interplay between these two numbers. Usually it will be the weak one, because the weak one is more permissive, so you have more choices. What time is it now? Time to end now. 10:40 now. Exactly 2 hours. So I will say a few more things, but nothing complicated. So we have this nice characterization by Zhu. And of course one part of the characterization comes from here, right? The fact that if you can bound one type of covering numbers and then you bound the other, this comes essentially from there, right? So what is missing is why is this equivalent to bounded expansion? And so this afternoon I think I will just start with that. what I will show you, and it's not too difficult to show, it might be easier than this proof, I don't know, you tell me, is that if your covering numbers are bounded, then you will have bounded expansion. That is not too difficult to show. Well, I'll show that first thing this afternoon. And to close now, I'll just give a few remarks on this. Well, if you look at the proofs from the literature on different types of things, so the things we are not covering, which they use very often, are these things, topological grads, top grads, and there is another one which they call admissibility. So admissibility of D, I'm not going to define, but it's essentially an even stronger version of the strong coloring number. So it will be like this, but this is the lower bound for the strong coloring number. The reason, this is maybe not so interesting in itself, but the reason is that this actually also, you can bound this by a function of this. So this is essentially based now not on having path, but you look at the disjoint path. When you go back, you want all your paths to be disjoint. So you want the maximum number of vertices you can reach using disjoint paths. That's just, it's not important. I was thinking whether I would cover this, but it's just too many notions. But this is very useful as a tool because this has a nice algorithm to compute this.
So what's the parameter called? I can't.
Admissibility.
Admissibility.
This is called the admissibility. But we are not going to use it. I just might sometimes say that, oh look, this thing is proved using admissibility. So,
What is the definition?
well, I don't want to give you the definition. Too many definitions, no? You're okay. It's not very difficult. Okay? It's not very difficult. You're just looking at disjoint paths instead of any path. That's anyway. The fact that this is a disjoint path actually gives you, I think, maybe it's related to flows or something like that. So for those who know algorithms, you can compute this. I don't think you can compute in polynomial time, but you can give some good approximations. You can give, I think, a D approximation in polynomial time. And since you will have here this similar type of bound, you will have admin to the power D or something like that. So you can use this to actually construct some strong coloring and weak coloring algorithms, which are not too bad. Which will be, factor some polynomial. Well, if you know this was constant, this will remain constant. So yeah, we can kind of in practice compute these things. That's what I'm saying. Not exactly, I think it's NP-complete to compute it exactly, but you can take some approximations. Okay. Right. And this is for any graph. But for graph classes of bounded expansion, you can even do better. You can get it in some huge function, which depends on the class. But, like linear time, but with a big function which depends on D and the class of graphs. And you can compute it exactly. But that doesn't matter. Just to tell you that okay, we can actually work with these things. Okay, maybe just to close, what will be, so next we will see applications of these things. What will be the types of applications? Why is this nice? I mean, the first thing is you can now apply this. This is a characterization, the theorem of Zhu I told you. So you can apply it to show that some particular graph class has bounded expansion. And for example, one very nice one is these geometric graph classes. So you put some objects in the plane, for example. Okay. And you make a graph out of it. So any object, like every cycle here becomes a vertex. Okay. And you can prove that using these orderings. So essentially what they do is you order them by decreasing radius. Let's say some of them have small radius. You order them by decreasing radius, and this will give you a good coloring number. And so, okay, under certain conditions, you want that These guys don't intersect too much, which means that at any given point of the plane, you should not have too many of these objects. If you can bound this by a function, say, t, for example, you cannot have this kind of things, then you will have a huge clique. So if you can bound this by t, then you order them by decreasing radius, and you get a nice covering number, which means that they have bounded expansion. So this is an application of this. For example, in fact, planar graphs, you can do planar graphs, because planar graphs can be represented as, intersection graphs of disks touching disks. So every planar graph has a representation, geometric representation like that. Okay. So you see that, and any two disks touch in just one place. So that means every point is covered by just at most two disks. So they're really touching, not overlapping. But you count this as an intersection when they touch. So every planar graph can be represented like that. This shows that this number I was telling you, t, is at most 2. And you order these things by decreasing radius. And you get, this shows that planar graphs have bounded expansion. So this is one application.
This is work of Zoding-Joule, you said?
No, this one, no. Well, no, the characterization is Zoding-Joule. The big theorem that says that bounded expansion if and only if the coloring numbers are bounded. This is 2009. So you see, this bounded expansion was invented, I think, in 2003, if I remember well. So they first came up with the first definition, some other characterization, and then Zoding came up with this coloring characterization, if I understood well the history. Another application is coloring exact distance graphs. So I have worked on this a little bit, by the way. So you take your graph and you want that vertices receive different colors if they are exactly a distance d apart from each other. It's not obvious to bound these chromatic numbers, but when your graph class has bounded expansion, you can use these coloring numbers to give some good bounds on the chromatic numbers for graphs of bounded expansion. This is another application. There are some algorithmic application. So maybe on tomorrow or Thursday we'll mention algorithmic applications, especially there are approximation algorithms for domination parameters, distance domination. These are quite nice. I hope I will have time to cover this. Nice arguments. Easy algorithm like greedy algorithm, and then you use the coloring numbers to give the approximation factor. And what we will see this afternoon is the neighborhood complexity and profile complexity of the graph, which actually give another characterization. Neighborhood complexity, this is related to, somebody was mentioning VC dimension yesterday, so this is very much related to VC dimension. So I will define these things this afternoon. And I think these are very nice things which follow from this weak coloring algorithm, strong coloring. So this is essentially the way how your neighborhoods in your graph can intersect. So it's all possible when you have a set X. You know, how many subsets of X can be neighborhood of a vertex? How many of this? And we will see that this is bounded for graphs of bounded expansion. This will be proved using these color numbers. And this will have applications, by the way, in kernelization. So in requirement size complexity. Shidesh will tell us about that at some point. Yeah. So these are the things that I hopefully will have time to convince you that these are interesting in the following lectures. Let's stop now. Thank you. Are there any questions?
So we can restrict the paths in different ways, right? For example, strong gathering number make sure that all internal bodies are right to DA.
Yes.
And weak make sure that all are right to DJ.
Yes.
But we can also say that all must be at most VJ or at most DA. So we need to give a different notion of possibility.
Good question, I don't know. Well, isn't it the same as reversible?
I thought, but I couldn't.
I think it's the same as reversible. you're saying is that now you're reaching VI from, sorry, you're still reaching VJ from VI,
Yes, yes.
but you're in the other
That direction is there, but
Any other comments or questions? So let's have a break, I suppose. Tea is probably there.